Okay, now I'm going to encourage you all to draw along with me. I've stopped sharing the drawings as separate images just because I really want you to draw along, follow along with me. Again, this is something that is in the science, in the literature, as far as helping you understand concepts, especially processes, which is what we typically will draw out and illustrate. So it's really important to put your pen to paper, right? So not typing it or just taking a screenshot, but actually drawing out together as a class. And so make sure that you're doing that, following along as we draw. The other piece is if you do miss anything, you can go back into the recordings and just fill in what you missed, right? So these won't be shared as separate images, but they will be in the recording so that you can go back if you did miss anything or if I was perhaps moving too quickly. Okay, so let's go ahead and start here. Where we left off was looking at homeostasis. So we're going to pick up there and actually illustrate what that process looks like. What we left off describing about homeostasis was that it was never actually done, it was never actually complete. Right? It's not necessarily an endpoint or a destination. It's a continual process, right? We're always striving to maintain certain variables, and that phenomenon is known as homeostasis. So let's look at an example of that here. Okay. So the example that we're going to illustrate is really a car, right? So we're going to start with our car. It's going to be attempting to climb a hill, which is going to be really important as far as what's taking place, but we're going to start out drawing it here at the bottom of the hill, okay? And please excuse my car. It looks nothing like today's car, but hopefully it can make do, right? So here's our car, it's at the bottom of the hill, and this is where we're going to start out. Now we want to illustrate as well what speed the car is traveling at while it's on this flat surface, right? This flat part of the hill. And so that is where we dial in our set point, okay? So we're going to describe the speed down here, our set point. And that will actually be about 60 miles per hour. Okay, so this is where we start off. We want to keep our car going at 60 miles per hour. And so we can consider that variable our set point, and we're going to dial it in while the car is here on the flat. Now the car is going to reach the foot of the hill, and here's where it's going to attempt to actually ascend the hill, right? So it's going to attempt to ascend the hill or start moving upward, right? Start climbing the foot of the hill here. And so we're going to draw our car in slightly higher on this incline. Oops. Wheel should be round, not square. Okay. Right, and so here's our car slightly higher on the ascension. Now, the speed is going to be a little bit slower, right? I'm sure we can all appreciate that if we're trying to go up a hill, as we begin ascending that hill, we will naturally slow down. So the speed here is about 55 miles per hour. All right, and because the speed has decreased below our set point, this is going to set off an alert, which is called our error signal, right? So now that 55 miles per hour is below our 60 mile per hour set point, this will set off an error signal, right? So there's a decrease in speed, which sets off an error signal. Okay. Let's continue on going up the hill. So our car keeps moving. And what has to happen in order to maintain our set point is that we have to increase the gas flow to the engine. So that's going to be somewhat of the corrective measure for the error signal. So that's going to be the next step here, right? We increase gas flow to the engine. and that will automatically increase the speed. Okay. So now we can look at how our car begins to accelerate in speed once again, simply because of that reflexive action. We drop below our set point, that set off an error signal, and now we increase gas flow to the engine. So that should, in theory, correct that error signal and increase the speed. So if we look at our car a bit further up the hill here, okay, it is now at a speed of about 58 miles per hour, which means that we're beginning to increase the speed, right? So we've increased the speed to about 58 miles per hour. Is our error signal off yet? No, not yet, because we're not back at 60, but we have somewhat decreased our error signal, right? So we've slightly decreased the error signal. But we haven't turned it off completely. All right, now if we follow this just a bit more, now we're at the top of the hill here. Okay, once again, we've got our car up here all the way at the top. And here we're back at set point, right? Really important. We're back at set point. We're back at 60 miles per hour, which we said is our set point value. And so here we can turn off the error signal. Okay, we can turn off the error signal. All right, so can we see how we have dialed in our set point at the bottom here, because this is a variable that we would like to maintain. And that is also true with regards to homeostasis. When we have a desired variable, whether that be blood pressure, body temperature, blood pH, this is a variable, or this is a value of that variable that we would like to maintain constant. And so the body will have checks and balances. In this case, with our car, that would be gas flow to the engine, as well as the error signal. Those are the checks and balances that are going to identify when we shift away from the set point, and also work to get us back towards that desired variable or value, for our variable. Okay, now let's see what that looks like as far as a graphical representation here at the bottom. So if you look at our speed at the bottom here, oops. Okay. So here is our little graph at the bottom. On the axis here is our speed, which we're starting at about 55. Right, 55 miles per hour. Okay. Whereas we would like to be is closer to 60 miles per hour. Okay, so we start off, let's draw this in another color. We start off at 60, right? And then we decrease, okay? And then we're back up again. Oops. Let's try this again. Okay, so we start off at 60, drop down to about 55, and then we eventually get back up to 60. All right, and so where we want to be here is 60. Where we end up dropping down to, this is going to trigger our error signal. So it's really important to notice that the degree of the error signal is going to be the degree with which we are away from the set point. So here's where we would like to stay, our set point value at about 60. And then here is our error signal, the degree of our error signal. So because here we're really far away from that set point, we're going to have a really large error signal. Okay, as we begin to increase gas flow to the engine, notice that the error signal gets smaller and smaller and smaller until it is eventually turned off. So the degree of the error signal is the degree with which we are away from our original set point value. All right. Okay, and we're actually looking at speed against time here. So let's just fill this in. So it's how fast the car is going, and then times here. Okay, on the X. All right, so this is our illustration as far as our homeostasis example. We're going to talk about these different terms, set point, error signal, and we're going to describe them. But I really want to reiterate this example as far as how homeostasis comes about, right? It's never fully done. It's always a process of striving to maintain these set points, but we have our checks and balances, our error signal, which tells us when we move away from that, and then our corrective measures, which try to get us back to that set point. All right, any questions at this point? Any questions? Okay, now I'm going to give an additional minute just in case you're finishing up. And then we're going to keep going. All right. Okay. So okay, so here's again that same example, just to reiterate what we just said there. These are our various terminologies. So the regulated variable, here it was the speed, but in our body, this can be all of the various variables that we talked about: body temperature, blood pH, our blood composition, blood volume. Those are all examples of regulated variables with which the body wants to keep at a specific value. The set point is where we want to keep that value. So for example, blood pressure, right? Blood pressure is typically anywhere from 120/80 to 130/90. That would be considered a set point for the variable blood pressure. And so the body would do everything in its power to keep the blood pressure at that specific range, okay, excluding any pathology. So also in our example, some of the other terms we want to think about are negative feedback. Now, negative feedback is the self-correcting response if a variable tends to move away from set point. So if a regulated variable decreases, in our example with the car, that would be the speed. If the speed decreases, that's going to result in that error signal going off, the gas flow coming to the engine, the speed going up, and that loop is called a negative feedback loop. So negative feedback is that self-correcting measure that will help to bring us back to the set point value. The error signal, we said, is the difference between the set point and the current value, right? How far away that current value is from the set point. And again, thinking back to our example with the car, when the speed decreases below 60, that sets off an error signal, and how far away it is from 60 would be the degree of that error signal. So there can be degradation or different quantities of the error signal, again, depending on how far we are from the set point. Now we can think about this in our actual physiology. So here's another example. This one is closer to our internal physiology, and this is regarding our blood glucose levels. So blood glucose, otherwise known as your blood sugar, should also be maintained within a very short, small window, very tight window. And typically that is about 100 milligrams per deciliter, right? 100 milligrams per deciliter. And this would be a fasting value, just FYI. So typically, if you've woken up in the morning, you haven't had your first meal, you do your, finger pinprick, and you measure how much glucose is in your blood, that number should be around 100 or even lower, right? Lower. So here we see that if that rises, okay, let's say you had a really large meal, and so your blood glucose rises, that is going to trigger an error signal. The regulatory mechanisms to correct that change are going to be initiated. And for our physiology, that's going to be our insulin levels rising. Insulin is going to trigger the absorption of that glucose so that it can be removed from the blood, taken up into the cells, and used or utilized to make ATP, to make energy. So that is the mechanism by which we can decrease that blood glucose and bring it back to its 100 milligrams per deciliter, which is the set point for blood glucose. All right, so as we begin to initiate that mechanism, we're going to decrease the error signal once again, and that will bring us right back to 100 milligrams per deciliter, which is our normal glucose value. So we can see how that example with the car can also be translated to all of the variables inside our body, and it's going to work the exact same way. At a set point, we've got a shift from the set point, which can be up or down. By the way, it can be up or it can be down. If blood glucose drops, right, if someone becomes hypoglycemic, that's going to trigger a different type of error signal, which is going to serve to bring it back up and correct that error signal and bring it back to the set